Hi, my name's Will Krawczyk, Scientific Services Manager at Chemical Computing Group. Today I'd like to introduce MOEsaic as a web browser application for interactive SAR analysis. In this session we'll see how to upload a dataset and then perform some basic searches. Number 1, to identify if a given chemical motif is important to activity, and then number 2, to find similar compounds based on their Tanimoto score. So let's get started. This is the launch page for MOEsaic, where we select the dataset we want to work on, which can be in CSV, MDB or SDF format. The database would typically include structures, unique identifiers, descriptors, and the property that we want to optimize, which is typically activity. Today we'll use the COX2 dataset. Once we select the dataset, we then need to configure it. And we can select the data that we want to appear in MOEsaic and ensure that the correct category is assigned for each data type. So for example, compounds are recognized as structures. MOEsaic automatically assigns these categories. We just need to ensure that everything's correct and that no edits are required. We can also set the primary activity fields, which is important when we have multiple activity values in our dataset, as we do today. So here you'll see we've got COX2 and COX1 activity. For me, all I need to do is change COX1 to become an activity and then click Start to start the session. And in the background, MOEsaic will calculate properties for every structure in the dataset, such as S log P, molecular weight, and so forth. And it will also fragment every structure in the database so that we can perform calculations such as matched molecular pair or free Wilson analysis. The concept here is that we front load the calculation so that then we can run any query we like rapidly without having to wait. So before we get started, just a quick overview of the layout. We've got 4 main panes. We've got reference, structures, properties, and plot. On the side, we have an overview of the dataset and options for filtering. So let's go through these one at a time, starting with the reference pane, which displays the reference ligand. By default, this would be the compound with the highest activity, but I'll show you how to change this in just a moment. We also have space for a highlighted or a query ligand, but there's nothing there just yet. We can use the reference pane to perform substructure searches, similarity searches, interactive match molecular pair queries, and sketch new ideas. Below the reference pane sits the structures pane that contains every structure in the dataset together with customizable fields. And you'll notice as I hover over one of these structures, it becomes the highlighted structure in the reference pane, allowing us to do a pairwise comparison. Supporting the pairwise comparison is the properties pane, and this is synced again so that as I hover over each of these different structures, the properties of the highlighted structure update and are depicted by the blue dot, allowing us to compare that to the reference structure, which is depicted by the red diamond. We get a numerical readout of the properties plus a plot. The plot is currently displaying the oral drugs model, whereby ideally these data points would fall within the coloured bars. I can change this to the sweet spot model, whereby ideally the data points would fall in the centre region of the plot, shown here in yellow. I also have options that I could configure my own custom models. Below the properties pane sits the plot pane, which allows us to plot in multiple dimensions. So we can use the traditional X and Y values, axes, to display our properties, but we can also use color. So for example, we could display the chemical series, which is encoded in our dataset. I could also use size, opacity, and symbols. So I'm just going to zoom out slightly to make our data points a little bit smaller. So when loading in a fresh dataset, typically I like to make a visual inspection of our structures, so I'll just maximize that structures pane, and we'll see that many of these structures contain a phenylsulfone. So to make this task of visual inspection and all of the subsequent tasks that little bit easier, what I'm going to do is just align all of our structures to that common phenylsulfone. So I can do that from the reference pane by clicking Define Pane Alignment, which opens a sketch tool with different atoms and bonds, and then various options that allow us to manipulate the view and orientation. So I'm just going to use the reference structure to isolate the substructure of interest. I will perform the alignment, so I'm just going to orient the phenylsulfone as I want. And then I noticed in the dataset that sometimes we get a carbon and sometimes a nitrogen in this position. So I'm just going to go ahead and add in a wildcard there, and then I'll align. And every structure that contains that phenylsulfone will be aligned accordingly. Now that we saw that many of these structures contain a phenylsulfone, a common question might be, is that substructure important to activity? To answer that question, we can perform a substructure search. So here I'll go ahead and query, whoops, I just missed the, so I'll just grab that phenylsulfone just there and perform that search, and that will create a filter that appears on the left-hand side. And you can see here that 97% of the dataset contains that phenylsulfone. Now, to answer the question, is it important to activity, remembering that we're plotting here on the y-axis COX-2 activity, our primary activity, I'll just toggle to those structures that do not match, and we see that not many of these have been explored and they don't seem to be particularly active. So that phenylsulfone does appear to be important to activity. Now, we've touched upon the filters here, but we can dive a little deeper and think about selectivity. So we've got both COX-2 and COX-1 activities. So let's use this to find compounds that are more active on COX-2. So I can use the slider, but I'll perhaps just type in here. So we want compounds that are active on COX-2, less so on COX-1. The filters are stackable, so if I want to think about bioavailability, I could also add in TPSA as an example, and perhaps I just want to focus on some of the more promising compounds by scaling back TPSA a little bit. I have options that I could also disable these filters if I don't want to use them, and I can also collapse them too if I'm running out of space. So, as mentioned, the default reference structure would be the most active molecule in the dataset, but sometimes we want to change this. Perhaps we want to compare similar molecules. So one option to change that would be to use the magnifying glass. If I knew the identifier, I could select it here. I could also double-click any structure that you see in the dataset, and that automatically becomes the reference structure. But what I'm going to do in this case is use the plot pane, and I'm going to toggle on my Lippi levels. So lipophilic efficiency, the all-important Lippi level 6 is displayed here in red, and ideally I'd find promising compounds that sit just above that line. In this case, we don't have many, we don't have any that sit above Lippi level 6, but some do get quite close. So let's just take we'll zoom in on this little region here and perhaps select one of these compounds. So I'll select this and make it the reference compound, so that becomes the reference. And from here I might be interested to find other compounds that are similar to that new reference. So for that I'll perform a similarity search. So I'll just toggle here in the reference pane to Sim. I could select a subset, but I'll just query the entire molecule by clicking Search. And we see here that a filter has been added together with a similarity index that ranges from 0 to 1, comparing the fingerprint of that's been generated for the query to the fingerprint of every structure in the database, whereby that similarity is scored according to a Tanimoto score, with 1 being very similar and 0 being very dissimilar. The default cutoff is 85%, and I can see here that we're returning 13 different compounds. But perhaps we'll just make this a little bit more stringent, and here I've identified the 4 most similar compounds to our reference. So with that I could simply select those, and I could write that selection to a new tab so that I can come back to it in the future. To aid my memory, I could also give this a more meaningful name, so perhaps I'll call this Promising Compounds, as I say, just to jog my memory when I come back to it. And with that, it brings us to the end of today's session, where we explored the MOEsaic interface. We saw how to set up a session, perform a substructure search to identify if a given chemical motif is important to activity, and then similarity search to find similar compounds based on their Tanimoto score. If you have any questions, please do reach out to us at support@chemcomp.com.